Okay, so welcome back to this next video in which we are discussing the two-pore domain potassium channels. Okay, right, so we've studied the role of these two-pore domain potassium channels in normal physiology and how important they are in the build-up of the electrical potential difference across the cell membrane. Okay, what we now want to discuss is their actual structure. But before we do that, let me just discuss other names for these two-pore domain potassium channels. Okay, they are also called the leaky potassium channels, or the background potassium channels, or the baseline potassium channels. All of these are other names for these two-pore domain potassium channels. These are, if you like, more physiologist names for these potassium channels, whereas the two-pore domain potassium channels is the sort of pharmacologist name. Okay, right. So let's now have a look at the structure then of these two-pore domain potassium channels. Okay, so let's start by drawing a cylinder that's sitting within the phospholipid bilayer. So this represents the cell membrane, the two leaflets of the phospholipid bilayer. So the outer layer of phospholipids and then the inner layer of phospholipids. Okay, and we've got this ion channel now sitting in this phospholipid bilayer here. Okay, so it's always a good start when drawing an ion channel to draw a cylinder like so. Okay, right, and then we've got the pore going down the center there. Now basically these two-pore domain potassium channels are made up of two proteins. So I'll divide it into two like so. So you have two proteins dimerized together to make the entire pore basically. So it's a dimer. Okay, now what I want to do then is put out a single one of these proteins now. So I'm going to separate off one half of the ion channel, if you like. And I want to have a look at the structure of this protein. Specifically, I want to look at how it spans the membrane. So I want to study its membrane spanning topology. Okay, so let's have a look at this. So here's another picture of the phospholipid bilayer. And this is the extracellular fluid side, and this is the cytoplasm side here of this cell membrane. Okay, and then you have the amino terminus of the polypeptide within the cytoplasm. So we're now drawing the structure of this polypeptide. So here's its amino terminus. Then what you have is a membrane spanning alpha helix that will span the membrane. Okay, then you have a rather large loop, which I'll name in a moment. Then we have a loop that tries to get back through the membrane but fails. Then you have the second membrane spanning alpha helix, then the third, then another one of these loops that tries to span the membrane but fails, and then a fourth membrane spanning alpha helix, and then you have the carboxylic acid terminus of the polypeptide intracellularly. Okay, so let's name up the different components of this structure then. Okay, so we'll start with the membrane spanning alpha helices. So here's a membrane spanning alpha helix, here's a second membrane spanning alpha helix, a third, and then a fourth membrane spanning alpha helice. Okay, and these membrane spanning alpha helices are labeled up. M1 is the first membrane spanning alpha helix, so the one that's closest to the amino terminus. The second membrane spanning alpha helix here is then called M2. Okay, the third you can probably now guess is called M3. And then the fourth over here is called M4. Okay, next up we'll label up these loops that try to span the membrane but fail. Okay, so these portions that are now highlighted in red, these are called the pore loops, okay, or the pore domains, and the reason for this is that they are going to line the pore on the extracellular side. Okay, so these are called the pore domains. And this is why these potassium channels are called the two-pore domain potassium channels, because each subunit of one of these two-pore domain potassium channels has two pore domains. If you look at the structures of the other types of potassium channels, such as the inward rectifying potassium channels, the voltage-gated potassium channels, the calcium-gated potassium channels, they will only ever have one of these pore loops. Okay, these ones are special because they have two pore loops or two pore domains. So these are also called pore loops. Okay, and basically each one of these subunits that makes up the total potassium channel here will contribute two pore loops into the pore. So basically this one that I've highlighted in purple will supply both of these pore loops into the center of the pore, so they will be right in the center. So if I show this again, okay, so let me draw the channel now from above basically. Okay, so here's the channel view from above, and it's made up of these two separate proteins. Basically these two pore loops of this single protein will line the center of the channel basically at the extracellular side. They can only line it at the extracellular side because they're only on the extracellular side. They don't make it the full way through the membrane. Okay, so here are these two pore loops of this protein, and obviously the other one will then have two pore loops as well, which means that the whole pore is lined by these four pore loops. Okay, right. So that's the characteristic feature then of these two pore domain potassium channel subunits. Okay, then this large loop that we have between the M1 and the first pore loop, and in fact before I talk about this blue loop, let me just give you the symbol names for these pore loops. So the first pore loop is called P1, and then the second pore loop here is called P2. We're going to need the name of this first pore loop to understand the name of this. Okay, so this blue loop then that's extracellularly is just called the M1 P1 loop, and that makes complete sense now because it's in between M1, the first membrane spanning alpha helix, and then P1, the first pore loop here. Okay, right, so that's the structure of these subunits that make up these two pore domain potassium channels then. What we now want to discuss is how many different two pore domain potassium channel subunits are there. Okay, and for this I need to give a reference for where I got my information from. Okay, because this isn't something you can just find in the textbook. Okay, so I got this from a fantastic review by someone called Honoré. Okay, and I hope I pronounced his name right. So it's a French name, so it's got an E acute on the end, which means that you pronounce it A at the end. Okay, so Honoré, and I think his first name was Eric, so Eric Honoré, and it was written in 2007. So reasonably up to date. Okay, so I'm now going to tell you about the different two pore domain potassium channel subunits that are present in humans. Now you might be sitting there thinking, well, wouldn't it be beautifully simple if there was just one subunit which was the two pore domain potassium channel subunit, and all you had to do was build two of these and then stick the two of them together, and then you have your two pore domain potassium channel. But unfortunately it's not that simple. Okay, instead there are 15 known human two pore domain potassium channels. Okay, and two pore domain will from now on just be abbreviated to 2P. Okay, so to 2P potassium channels, or two pore domain potassium channels. Okay, so let me now discuss the naming of these 15 human two pore domain potassium channels then with you. Okay, so their naming is reasonably sensible. There are gaps in their naming, and the reason there are gaps in their naming is because people have been researching these types of potassium channels which have this sort of a structure in all sorts of different animals, and where there are gaps in the numbering, it's because that number, two pore domain potassium channel, isn't actually found in humans. Okay, so I'm only going to tell you about the ones that are found in humans, so there will be gaps basically. Okay, the other confusing thing is that there are many different names that people use for these things. So I'm going to tell you the two sort of official naming systems, and then we'll talk about the names that actually everyone uses, which are much more difficult. Okay, so the official names are very, very simple. Okay, so you start off with a K for potassium channel, then you put a 2P for two pore domain, and then we have the two-pore domain potassium channel 1.1. Okay, so that's a first subunit that has this sort of membrane spanning topology and is capable of dimerizing together to form a full two-pore domain potassium channel. And then we go on. Okay, so there is also K2P 2.1, K2P 3.1, okay, K2P 4.1, okay, K2P 5.1, okay, and we continue on. There is K2P 6.1, so I think I will write all of these out because it'll help us later, because they all have their other names, so we do need to write them all out so that I can put their other names next to them. Okay, so then we've got K2P 7.1, so the naming is going very nicely at the moment. Okay, however, there is no K2P 8.1, at least not in humans, so I'm going to leave out K2P 8.1 and we'll go straight on to K2P 9.1. Okay, then we've got K2P 10.1, K2P 11, actually no, there's no K2P 11.1, sorry. We go straight past 11 up to 12, so there is K2P 12.1, okay, then there is K2P 13.1. Okay, so K2P 11.1 has the same problem. It's not found in humans, basically. It exists, but it's not found in humans. Okay, then again, there is no K2P 14.1, so I'll come up here now, and we go straight on to K2P 15.1, and then it goes nicely from then on. So we've got K2P 16.1, K2P 17.1, and then all the way up to K2P 18.1, and that's now 15 human two-pore domain potassium channel subunits now named. Okay, so they all have this same membrane spanning topology here, and they can all dimerize to form potassium channels. Now, there is another naming system that is also quite official and is quite a nice naming system. Okay, so we'll go over this one now. So these are also called KCNK channels, and you will see the KCNK nomenclature quite a lot, but the naming is exactly the same as with these. Okay, so you have KCNK1 is K2P 1.1. You have KCNK2, which is K2P 2.1, and then it will go on. K2P 3.1 is KCNK3, K2P 4.1 is KCNK4, and it's perfect all the way down. So that's not too difficult. Okay, right, you just have to remember there's no number 8, and there's no number 11, and there's no number 14 either. Okay, right. Now it gets onto the more difficult naming system. But before we talk about the difficult naming system, I want to talk about the different properties of these two-pore domain potassium channels. Okay, right. So they are basally opened potassium channels for the most part. Okay, so they're usually open all the time. However, there are stimuli which can increase the amount of time that they will spend open, or increase their conductance, because, you know, these are proteins. They are flexible proteins, so they will be moving around from time to time, so they don't spend all of their time conducting potassium ions. It would be foolishly naive to expect them to just sit there as this rigid structure that never changes. Occasionally, you know, it might just maneuver itself slightly, which means that it, for a moment, occludes the channel. Okay, so there will be a certain open probability for the channel. It will have a certain probability that if you look at it at any one time, it will be open and conducting potassium ions. So certain stimuli can increase the probability that it will be open at any one time. They can increase what's known as the open probability of the channel, or PO. Okay, so I'm going to discuss the gating of these channels, and this is why I've had this discussion of open probability, because you might think, well, hang on a second, aren't these things always open? And yes, they are, but sometimes they will close, okay? They are not a rigid, inflexible structure. They are moving, okay? And although they do spend a lot of their time open, they will sometimes adopt conformations that are closed, and certain stimuli can increase the likelihood that they will be open at any one time, basically increase the amount of time that they spend in the open state. Okay, right, and some stimuli can decrease the amount of time that they spend in the open state. So, we're now going to discuss the different things which can affect the different two-pore domain potassium channels. Okay, so the first thing is that some of these will be mechanically gated. Okay, so I want to highlight which of these channels are mechano-gated and therefore are opened or closed by mechanical stimuli, and usually they're opened by mechanical stimuli. Okay, so the mechano-gated two-pore domain potassium channels are K2P 2.1, which is an extremely famous two-pore domain potassium channel. K2P 2.1 or KCNK2, and we'll see another name for it later, is the most heavily studied of all of these potassium channels, and it's mechanically gated. Then K2P 4.1 also shows mechanical gating properties, and finally also K2P 10.1. Those three are all mechanically gated. Okay, so those are the mechano-gated ones. Then we've also got the ones which are alkaline activated. So these are activated by low concentrations of protons, i.e. they're going to be opened by alkaline pHs, or at least they're going to have their open probability increased by alkaline pHs. Okay, so we'll highlight these ones in turquoise. So examples of these are K2P 5.1 and then also